My name is Jeff Wolschlager. I am the VP of Composite Technology at Altair Engineering. This is a short course on the introduction to multiscale designer for continuous fiber reinforced material product forms. The short course involves 3 video sessions. The first 2 were prior completed. The first video session covered multiscale material model development using the forward process. The second video covered structural simulation using multiscale material models, specifically the multiscale material model that we developed in the first video session using the forward process. And now this third video session will cover multiscale material model development using the inverse characterization process. So just a different way to develop multiscale material models. We will be going through in detail the inverse characterization process for linear and nonlinear material characterization, and we'll offer a little bit on verification of multiscale material models at the very end. So let's get started at the topic of interest for this video session, multiscale material model development using inverse characterization. By way of review, the inverse characterization problem is stated as given the homogenized ply properties, we want to calculate the constitutive matrix and fiber properties that will give me the homogenized ply properties back again. This obviously involves an optimization loop where we make an initial selection of matrix and fiber behavior. We perform a forward analysis to get the calculated homogenized ply behavior. We compare that forward calculated homogenized ply behavior to the exact experimental data that's provided, for which we can assess the error between the two. We can use that error to make a determination as to which direction we should make our next selection of fiber and matrix properties, perform another forward homogenization to get the next iteration of homogenized ply calculated behavior, from which we can compare against the experimental data again, calculate the error, and so on, and keep doing this until we achieve a tolerance which is within an acceptable limit. So this process produces highly accurate material models that are good for detailed design and certification efforts. No better way to go through the inverse characterization process than to run an example. So we will be inverse characterizing a NIAR agate T700-2510 unidirectional material. The material data reports that you can find on the NIAR NCAMP agate website are publicly available for this and many other materials, and the material data reports look like what I'm showing here. Some information that you'll need to grab out of those reports are the physical information, physical property information about the product form itself, usually the nominal cure ply thickness, the nominal fiber density, nominal fiber area weight of the particular product. You'll also need to grab the stiffness and strength data at whatever given temperature you're going to be creating this material model. In our case, we're going to be creating a room temperature dry, mean normalized material model. You could make a selection of anything else. That's just what we'll create. Could create a cold temperature dry, an elevated temperature dry, or wet for that matter. Material model, you could even create the material model as a basis model instead of a mean, or even a mean instead of a mean normalized, which we're going to be creating a mean normalized material model, which means all the data has been normalized to the cure ply thickness. It means we've been normalized to a particular fiber volume fraction, in this case, the 55% that we had before. It's important to state that while in general we want the all of the stress strain curves for all test specimens, in general, that data will not be available in many of the publicly available data reports. And you can assume that, while not completely correct, that all of the test specimens exhibit linear behavior except for the shear modulus and shear strength specimen, which is the IPS or in-plane shear specimen, which produces the shear stress for shear strain curve, which will normally be given in the data report somewhere, normally towards the end. I will give you this curve in the Excel spreadsheet shown here that just runs this equation to the best fit curve of all the data that they had. All other curves can be assumed to be linear. So while not exactly correct, gives us a basis for inverse characterizing all this particular data. Okay, so this chart just summarizes all the data extracted from this particular material data report. Any other material data report, this data could be extracted, and indeed you should take your time to go through this particular data report, which I have also provided in the file section to see where those numbers are and how I extracted these particular numbers. But we have the physical property data, the stiffness property data at room temperature mean normalized, and the strength property data at room temperature mean normalized. Okay, the inverse characterization process includes the same three steps that we had to do for the forward homogenization process. We need to create a unit cell, we need to characterize our material in the linear regime, and we need to characterize our material in the nonlinear regime. Only the linear and nonlinear material characterization will be done with the inverse process instead of the forward process. The unit cell will be exactly the same process that we did before. Okay, so we won't belabor the unit cell process. I'll just execute that quickly. So we're going to create a new model here. We're going to call it Uni Inverse. And we're going to start with our unit cell model development. Fibrous, we will use the continuous uni hexagonal pattern. We could enter in the volume fraction, which we know is 55, but we'll enter in the manufacturing data since it's a little more accurate. The 006 cure ply thickness, the 1.79 fiber density, and the 150 fiber aerial weight. And that ends up being a 55.0, give or take, fiber volume fraction. We'll stick with the default calculated meshing controls, and we'll click run to execute the parametric geometry and meshing of this particular unit cell inside HyperMesh in the background. So we'll give that a moment to finish up here. Okay, our unit cell has been created. Whenever we are done with the step, I always save that step on the step window and then go ahead and close out the step window. We can continue on with step 2, which is the linear material characterization using the inverse characterization process. The problem we're going to be solving here is, given the homogenized stiffness data, we want to determine the fiber and matrix constitutive stiffnesses that give us the homogenized stiffnesses back again. So pretty straightforward. What I want you to get used to is that we always start an inverse process with some initial forward process. So we just make our best guess as to something close. It doesn't have to be super close, but just anything close, just to get some numbers into the system to get us kind of started. So we will start this inverse characterization with a standard modulus epoxy and a standard modulus carbon fiber, which the T700-2510 is a standard modulus epoxy and a standard modulus carbon fiber product system. Okay, so we'll launch our linear material characterization. We'll start in our forward homogenization tab. The first phase is our matrix phase, and we'll go ahead and select a polymer, thermal setting polymer with US inch units, and we'll pick our standard modulus epoxy. For phase 2, which is our fiber, we'll go ahead and select a fiber carbon with our US inch units, and we'll pick the standard modulus carbon fiber. Okay, now that we've got some information loaded in the forward homogenization tab, go ahead and save that, and we can flip over to the inverse characterization tab, and you'll see that those initial values are loaded in for us automatically in the inverse characterization tab. So just a quick, easy way to go ahead and load that in. You could also load these in the inverse characterization tab through the constituent material database here, doing all the same thing. Okay, so now that I have some initial numbers loaded in for the fiber and matrix, we need to enter in our objectives. And our objectives are the homogenized ply stiffness property. So right from the data in the data report, we have the stiffness in the fiber direction, EX, the stiffness in the matrix direction, EY in tension, Poisson's ratio, the shear modulus, and then the stiffness in the fiber and matrix direction and compression. So we can enter those in and we will make those targets. And then we will activate certain parameters of the fiber and matrix that we want to change such that such that we hit the objective homogenized ply properties. So in our case, any active the number of active parameters must be less than or equal to the number of objectives. So if I have 6 objectives here, it means I can only have 6 or less active parameters. Well, I actually have more than that. Just in the fiber alone, you can see I have 6 here. And then in the matrix, I think I have another 3, that's 9. So I have 9 total numbers, which I don't know, but only 6 of them can really be determined. So normally we will assume that the Young's modulus and the Poisson's ratio of the matrix phase are known. And we'll also assume that the V23 of the fiber is known. So those are the 3 that we can't inverse characterize. So 9 minus 3 leaves me with 6 parameters that I can inverse characterize. And it turns out that these are the most important. The modulus of the matrix in compression is driving the matrix modulus of the ply in compression. The fiber modulus in the direction of the fiber, or one direction, is driving the fiber direction modulus of the ply in tension. The transverse modulus of the fiber, or E2 of the fiber, is driving the transverse modulus of the ply, EY. The Poisson's ratio of the fiber is driving the Poisson ratio of the homogenized ply product. The shear modulus of the fiber is driving the shear modulus of the ply product. And the fiber modulus in the direction of the fiber in compression is driving the modulus of the ply in the fiber direction in compression. This is just what parameters are principally driving what objectives. This is understood if you kind of look at a little bit of the Rowley mixtures equations, which, while not accurate, give you an idea as to what parameters are the most sensitive to other parameters, and/or just years of running these optimizations and knowing which parameters for unidirectional product forms drive which objectives. Okay, so we're going to define this entire optimization here, and then we will go ahead and launch it. So let's do that. We have our initial constitutive matrix and fiber stiffnesses entered already. Let's go ahead and enter in the test data, the experimental data for the homogenized ply itself. So EX is 18.209 e to the 6. EY is 1.219 e to the 6. The shear modulus GXY is 0.613 e to the 6. My Poisson's ratio in the 1, 2, or XY plane is 0.309. My compression modulus in the fiber direction is 16.284. And my compression modulus in the matrix direction is 1.471. Okay, we're going to make each of these a target. What's important about when you make them target is you notice that the weights are automatically calculated. All the weights are doing is getting these values on the same order of magnitude. If I'm calculating an error, so the functional tolerance is the sum of the error between all of the objectives. Well, if I have a Poisson ratio of 0.3, and let's say that my forward homogenization comes back as a calculation of 0.4, well, that's only an error of 0.1. Well, that number is so small relative to 18 e to the 6 that it would never play in the optimization. So what we do is we weight it by a number to get it up into the order of magnitude of 18 e to the 6. So I take the largest value and we weight everything to the largest value. And now everything is on an even par with every other. And so all of the optimization errors will be contributing at the same amount. And we won't have one weighted more than another. So that's an important detail that's automatically calculated for you. Like we talked about, for the matrix phase, the Young's modulus and Poisson's ratio we're going to assume are known, so they're not active parameters. But we can go ahead and make the compression modulus of the matrix an active parameter, and it will change from the initial value to any number between the lower and upper bound. We automatically calculate this based on your settings. I believe if you look at the settings, it's the auto-calculate percent bounds is at 25%. You can change that For the nonlinear, it's also at 25%. So you can change what that automatic lower and upper bound is, but it's 25% from the initial value, which is usually a good number to start with. Okay, so that's one active parameter. So I've got 5 left I can pick. So of the fiber phases, I'll pick the fiber direction modulus, the transverse direction modulus, the Poisson ratio in the 1-2 plane, and the shear modulus, and the compression modulus of the fiber. So that's 5 additional. That makes a total of 6. And you can see the lower and upper bounds were automatically calculated. What I will do is I'm going to open up the upper bounds of all the stiffness properties to the upper bound of the fiber, which is the largest it could possibly be, just to give the optimization a little more wiggle room to find a solution. That's normally what I do is the largest upper bound, I'll set the stiffnesses, not the Poisson ratio, but all the stiffnesses to the upper bound of the fiber upper bound. And I'll leave the lower bounds alone. So what we've set up here is an optimization problem where given these homogenized ply properties, which are the experimental data, we want to change the matrix compression stiffness and the fiber various stiffnesses that are checked here, change any of those 6 values to match this experimental data as needed. And if you get to a functional tolerance of 1,820, which is a sum of all of the errors between them, so that's very low if we're talking numbers of 18e to the 6. A sum of the error in the 1e to the 3 is very, very low. You could set this lower, but I just leave it as the auto-calculated value. I also want to mention that we will be using in the linear material characterization inverse process the truss region algorithm, which is a gradient-based algorithm. Gradient-based algorithms are really good with linear type problems. This is a linear type problem, and so we'll choose the truss region algorithm. In the second step, or the third step actually, the nonlinear inverse characterization, we'll be using the ant colony, which is a genetic-based algorithm. Genetic-based algorithms tend to be a little more efficient and highly nonlinear problems. But we have a fairly linear problem here. Well, it's linear material characterization. So we'll use the truss region or gradient-based optimization algorithm. Okay, we'll go ahead and run this optimization, and we'll let it solve. Okay, so the optimization has completed. You can see here in the optimization solution window, it took 4 iterations to finally complete. My final total residual error was 67. So while I told it to stop at 1,820, it actually got down to a total error of 67. So the difference between all these numbers weighted is 67. It's a very small error. You can actually see the weighted differences of each parameter here. And then the actual final active parameters right there. It's a little hard to read this, and so it's not important. What you can do is go ahead and close out this particular solver window. And what we're going to do is we're going to update our initial values, which will update the final active parameters, the solution, the optimization solution initial values. They'll update our initial values with the solution to the optimization. So those numbers will just be populated in once we do that. So we can close out. We'll update our initial values, and you can see the final optimized numbers that will give me the homogenized ply stiffnesses back again. We'll go ahead and save this data. And I believe if we go back to the forward homogenization, if we've saved it, the new values will be loaded in here, and indeed they are. So all of the optimized values are reloaded in. And let's finish this step by doing one last forward homogenization. So also while we're at it, I'm going to create a couple of laminates here. 3 laminates. We're going to do our all 0 again. We'll do our 90, all 90, and we'll do our plus or minus 45 symmetric. So minus 45, 45 symmetric. Okay, I'll just perform one last final homogenization of the optimized inverse characterized parameters. And this will give me the final result, which I should expect here, should be the numbers of the data. So I see the 18, 0.209, 0.309, 0.613 exactly as is, and then the compression 16,284 and the 1.471. So all of my numbers are checking out to exactly what I expect them to be. I'm very happy with this inverse characterization in the linear regime. So we can go ahead and save this step and close out to complete the step. Okay, we can move on to the step 3, which is the nonlinear material characterization using the inverse characterization process. So the problem statement we're solving here is, given the homogenized strength curves, although all of those curves are linear except for one, but given the homogenized strength curves, we want to determine the fiber and matrix constitutive strength curves that give the homogenized curves back again. So now we're working on the strength side of the picture. Okay, so the data that we have available to us, we have the longitudinal tension, which is the 0N tension, which measures my fiber brittle mode. We have the longitudinal compression, which is the 0N compression, which measures my fiber ductile or instability mode. And I have the transverse tension, which is the 90N tension, which measures my matrix brittle mode. All three of these tests are linear experimental tests within reason, not necessarily 100% completely true. But within reason, there can be considered linear tests for we don't have any data otherwise. But because of that, the linear nature of them, we can perform some calculations directly to obtain these. We don't need to actually inverse characterize them. We can actually calculate them directly. Normally, you would not have to do those calculations, but I think it's important and educational to do that, even to see how the ROM is actually working. So just while you shouldn't have to perform these calculations, I still think it's educational and instructive to do so. And we'll be using the forward homogenization approach to go ahead and perform those calculations. However, anytime we have a nonlinear experiment, so the in-plane shear 45 minus 45 NS tension specimen, which measures my ductile matrix, my matrix ductile mode, which is a nonlinear specimen, we have to have that exact curve. Since it's not linear, it's some nonlinear curve. We need to know exactly what the curve is. We won't be operating on the transverse compression or the 90N compression specimen. It also measures the matrix ductile mode. It's not required for this particular inverse. If you did have it, you would be able to inverse characterize beta values a little better, because I'd have two specimens at different volumetric strain. So this one at basically a 0 volumetric strain, and this one at a negative volumetric strain, which would allow me to inverse characterize the beta value. Remember, beta was the Drager-Prucker characterization that allowed the yield and tangent stress as a function of the volumetric strain, or as a function of J1. Okay, so again, just like the linear material characterization, in the nonlinear material characterization, I want us to get in the good habit of just starting an inverse with a initial forward homogenization. So we're going to perform 5 forward homogenization simulations, the LT, TT, IPS, LC, and TC specimens. Those were defined in video session 1. They're the same definition. So longitudinal tension is the 0 degree tension. Transverse tension is my 90 degree tension. IPS, in-plane shear, is the plus or minus 45 tension. LC, longitudinal compression, 0N compression, and TC, transverse compression, is my 90 compression. Okay, let's go ahead and define those. So we'll launch into our nonlinear material characterization tab. Since I selected my initial materials from the constituent material database, just like in the forward homogenization, I have some initial values input for the damage law of the matrix and the damage law of the fiber. So we can start with those initial values. Obviously, we'll have to inverse characterize those to exact test data, but we're going to start with 5 virtual simulations. And we'll define them here as our longitudinal tension, which is our specimen 1, our layup 1, which is my all 0. We will pull that to 2%. It has a delta T of minus 200. We'll take 10 thermal increments and 200 mechanical increments. Nothing changes here from video session 1, where we went through the details of defining each of these parameters for a virtual simulation. Simulation 2, we'll do our transverse tension. That's our 90-degree tension. So layup 2 is my 90, all 90. We will go 2% tension on that, minus 200 delta T, 10 thermal increments, and 200 mechanical increments. My third simulation will be my in-plane shear. That is my plus minus 45. So that's laminate 3. Laminate 3 is my plus minus 45, as you see here. We'll pull that to 5%. It's much more ductile, can go quite a bit farther. Still the same, minus 200 delta T, 10 thermal increments, and 500 mechanical increments. We always want to go in about 100 microstrain mechanical increments. The fourth test will be my longitudinal compression. That's my 0 compression. I'm back to laminate 1. Laminate 1 is my all 0. We're going to go minus 2%, minus 200 degree delta T, 10 thermal, and 200 mechanical increments. And my last one will be my transverse compression. That is my 90-degree compression. That's laminate 2. Layup 2 is my all 90. So we're going to go minus 5. That is a much more ductile test. Minus 200 delta T, 10 thermal increments, and 500 mechanical increments. Okay, if I go ahead and run these simulations in a forward, we will get the stress strain results for each of these virtual tests. And obviously, they will not match very well with the exact experimental data that we have for this T700 2510 because I have not inverse characterized the parameters in yet to the data. But if we look at where we're at here in Excel, just to show you that the virtual simulations were indeed run. I have some initial results for the stress strain curves of the 5 specimens. I'll flip over to the PowerPoint now just to show you the same curve. And so there's the same curve in the PowerPoint, and here is the data, the actual experimental data. And you can see what we already said, that it's not very close. So in 0 tension, I'm at 270 KSI, and the actual experimental data is 315 KSI. And in compression, I'm pretty close to 210 KSI. So this one is probably doesn't have to be inverse characterized in a lot, but it's not going to be exact at 210. And the yellow curve is the transverse tension. It's too low to see on the scale here, but it's not close to the 7,000. And for sure, the gray curve, which is the in-plane shear, won't be close to the actual curve that was given in the experimental data. So I need to handle each one of these curves kind of one at a time as we go through inverse characterizing these things to get them to match the data exactly and extract the critical parameters. So what I would suggest is that the next 2 slides detail the math, which again, you won't have to do in future releases. So we're working right now on our future release, which will be the 2023 year release and beyond, so about a year away. You won't have to do these calculations yourself. For now, you do. But I do think that these calculations are still instructive and educational because it gives you an idea of what the ROM is doing in the plugin. And I think that that's very important for intuitive use of these multi-scale material models. So I think I would suggest that it's important to just run these calculations. They're very simple calculations. They're not difficult at all. Let me just go through the calculations here, and then we'll do this actually in Excel, bringing up the mdsmat.dat file, which is exactly what the plugin would be using, and we'll operate on it. But maybe have these slides at hand if you are listening to the video, so you can, while I'm going through the Excel version of the calculations, you can kind of bounce off the actual equations here. So we can write stress equals C strain, or stress equals the stiffness matrix times the strains for the homogenized coupon. But I know the stress at which these failed, so I need to invert this equation. So inverting it, I get strain equals S stress, which S is the compliance matrix. I know the strain or the stress that the coupon failed at. In this case, it's the failure stress of the 0-degree coupon. And so I can calculate the strains, homogenized strains that this coupon is seeing through that calculation. Well, once I have the homogenized strains, we learned in video session 1 that I can amplify those strains through the A matrix, the amplification matrix of the fiber, to get what's going on in the fiber phase itself. And so if I multiply those strains by the fiber amplification matrix, I get the strains in the fiber. Well, once I have the strains in the fiber, I can simply multiply by the modulus of the fiber. You would normally do this in full 3D in the code, but we're going to make a simplifying assumption and just multiply it by the fiber modulus, do the 1D calculation, stress equals E strain. And I get the stress in the fiber, and that is the stress that gets entered into the parameter. That is the stress of our axial isotropic damage law. And then the strain is the strain at zero stress, which we just go 10% further than the stress at failure. And so it's just 1.1 times the strain of the fiber, which you see here is this number here. I do the same thing for compression. So instead of using the tension stress failure, I use the compression stress failure number, but run the exact same calculations, and I end up with the stress and strain values for this law here. That's all that law has. This is effectively doing dehomogenization. This is just taking the same 0 degree tension, ISO or ASTM standards, but reducing it differently. We're performing a few different calculations, and what we're really doing is performing the calculations as if I had a micro strain gauge in that specimen, which I don't, but we're amplifying these results, the homogenized results, which is what the ASTM and ISO standards talk about, not the micro results, which is what we're trying to get. So we're amplifying those results. We're just post-processing them through the multiscale material model, which is exactly what the plugin is doing in full 3D and in any finite element model. Okay, so these numbers aren't as so mysterious when we actually go to calculate them. Same thing with the matrix, the 90 degree tension, the matrix brittle behavior. So all of the brittle behaviors in the fiber and the brittle behavior of the matrix, all linear behaviors within reason. Not completely correct, like I said before, but within reason. So again, I have the homogenized strains. The only difference here is I need our homogenized calculations. I can, stress equals C strain. I can invert that. Strain equals S stress. The only difference is that instead of using a one direction stress for the fiber, the longitudinal tension or longitudinal compression specimens, I'm using a two direction stress for the transverse tension specimen. So I did just move the number over one spot in the stress tensor and perform all the same calculations. That allows me to calculate the homogenized strain of the 90 degree tension specimen, from which I can amplify to get the matrix strains. And once I have the matrix strains, this here full 3D, I can calculate the first invariant, which is the volumetric strain, by summing the normal strains. And once I have the first invariant normal strains, I can calculate the mean stress by the bulk modulus, which is easy enough to obtain. And then again, I can do a J1 at failure, which we're going to go 25% beyond in the matrix phase, the J1 at the initiation of the mean stress. So I can put those in fields 10 and 11 of the orthotropic damage and rate independent plasticity law, the mean stress and the J1 directly. So these numbers are not mysterious. All a C of 0 means is that a negative J1, so if J1 is ever negative, there can never be brittle failure. That's what a C of 0 means, which is correct and accurate. And then a W max of 1 just means I can have full damage happening. Okay, let's perform these actual calculations, and then we can put the numbers into our inverse characterization tab. So first thing we want to do is we want to start Excel, and we want to open up our MDS mat.dat file. So we're going to go to my material library, which is by default under my documents, Multiscale Designer. If your material file has been changed, or you've changed your default to some other local drive or even a shared network drive, just go to that drive wherever your local material model is. And again, you can see that Multiscale Designer is managing this folder file system for me, and I have all my materials in my material library. You can see I have quite a bit. But if you scroll down, we were creating a material called Uni-Inverse. And so there indeed is my Uni-Inverse material that I've been working with. And if I go under the mechanical folder and I look for all files, I will see my MDS mat.dat. And we want to open up this file, and I can tell you, open it delineated with space only, and that will bring every single number into its own column. Okay, well, here's the file that we looked at in video session number 1 when we did the forward process. And we're going to perform some calculations using these numbers, just like the plugin does when it's in full 3D. And like I said, while you shouldn't have to perform these calculations, I do think it really is instructive and educational. So let's go ahead and get rid of all the data up to the matrix, just because we don't need it. We'll get rid of data we don't need. And the first number of the matrix is the Young's modulus, the Poisson's ratio, and the Young's modulus and compression. All the other numbers we don't need. They're associated with the failure law. Okay, in the fiber, the first number is the modulus in the fiber direction. The second number is the modulus in the transverse direction. Then I have Poisson's ratios, 1, 2, and 2, 3. I have my shear modulus, and then I have my Young's modulus in the fiber direction and compression. All the other numbers are associated with failure laws, which we don't need. Okay, we'll get rid of the rest of the data up to the tension mode. And so the first matrix here is the homogenized L. Some professors use L as the stiffness matrix. I use C as the stiffness matrix. So this is your stiffness matrix indeed. We don't need the homogenized ENs, and so we can delete those. And then you see the A. So these are the amplification matrices in the linear regime. Phase 1 is my matrix, and phase 2 is my fiber. All of the P's are the nonlinear matrices. We don't need these for any of our linear calculations, so we can just go ahead and get rid of all the P's to the compression mode line. This is my stiffness matrix and compression. I can get rid of the homogenized ENs, and I can keep the amplification matrices again for the matrix and for the fiber, but now in compression, and I can get rid of everything else to the bottom of the file. It's just not necessary. Okay, so we're going to be operating on this data just as if the plugin was operating on it. So let's start with our 0 degree, the stresses of our 0 degree tension specimen. So the stress of that was, let's see, looking at our data, 315 KSI. And then zeros for the other 5 components. Okay, well, in order to get my strains, which I ultimately want to calculate the strains of the 0 degree specimen in tension, I need my compliance matrix, S. And that's nothing more than the invert of my stiffness matrix. So I can go ahead in Excel anyway. It's M inverse is the function to invert a matrix. I can just invert my stiffness matrix to get my compliance matrix. And we will just make these scientific. Good enough. I'm going to insert a column there. It was 1 over. Okay. So now that I have my compliance matrix, I can multiply that by my stresses, and I can get my strains. So the function in Excel is just mmult. So if I multiply my compliance matrix by my stresses, I will get my strains. Okay. So these are the strains, homogenized strains of the 0 degree specimen in tension. Okay, but that's not what I want. What I want is the strain in the fiber. I don't want the homogenized strains. I want the fiber strains. Okay, well, this is my amplification matrix. Actually, it is the transpose of the amplification matrix. So we need to just calculate the transpose of that for our particular purposes. So that's just transpose of this particular matrix here. And I'll put that into numbers. And you can see here that I get my, 0.4, 0.1 on the order of the 0.2 we talked about in the video session 1. Now, how do I get my strain of the 0 degree specimen in the fiber? Well, easy enough. All I have to do is multiply my amplification matrix by my homogenized strains. And I will get the strains now in the fiber. Okay, and so you can see, where I had, 17,000 microstrain, 17,300 microstrain. I still have the same 17,300 microstrain because I have a 1 0, 0, 0, which will always happen. But the other strains will not be exactly the same. Okay, I need to calculate the stress of the fiber. And the stress of the fiber is just going to be equal to the E of the fiber times my strain. Stress equals E strain. And so I get, 565 KSI, give or take, which is exactly the number I'm going to put into my form. And then I want to figure out what is my strain in the fiber with zero stress. So that's just 1.1 times the strain in the fiber at initial failure. So that's 1.9%, give or take. Okay, we're going to do the same thing now, but for compression, because my compression data is a little bit different. So what is the stress and compression of my zero specimen? It's 210 KSI. And then zeros for all the other 3D stresses. And again, I need to calculate my compliance matrix, and I need to invert my stiffness matrix to get my compliance matrix. And that allows me to calculate my strains of my 0 degree specimen as my compliance matrix times my stresses. Easy enough. And then I need to get the, I don't want the homogenized strains, I want the fiber strains. So I can come down here and get my amplification matrix of my fiber, which is just the transpose of what's stored. Put that into something that's a little more human readable. And that allows me to calculate the strains of the 0 degree specimen in my fiber, which is nothing more than the multiplication of the amplification matrix times my homogenized strains. Great, all is good so far. I've got, 1.3% give or take. I need the stress of my fiber now, which is equal to the compression modulus of the fiber times the strain. So I've got 376 KSI. Yeah, 376 KSI in the fiber and compression. So where I have 565 KSI in the fiber in tension, I got 376 KSI. Okay, and then if I want to figure out the strain at zero stress, it's just 10% beyond that, so about 1.4%. So these numbers are the numbers that I want to enter into the damage law exactly. So let's go ahead and do that while we're on the fiber phase. So we can flip over to the phase 2, which is our fiber phase, and we can enter in the tension and compression damage law properties exactly as calculated. So I'm going to have, what do I got here? I'm going to have 565 KSI. I'm going to be at 0.17%. I've got 376 KSI at 1.4%. Okay, so those are my inverse characterized fiber numbers. Okay, let's work on the matrix brittle behavior next. So we'll go back to our sheet here, and matrix brittle is in tension. So we're just going to start another column here for the stresses of the 90-degree specimen, which are 0, because I don't have a stress in the one direction, but 7,086 PSI in the two direction. Okay, and that allows me to calculate my strains of the 90-degree specimen as the multiplication of my compliance matrix times my stresses. And you'll see here that I've got about 5,500 microstrain in the two direction. But that isn't what I want homogenized. I actually want the strains of the matrix phase. So I need to calculate the amplification matrix of the matrix. So we'll just transpose our stored matrix here. Okay. And this will allow us to calculate the strains of the 90 degree of the matrix phase. And that's nothing more than the multiplication of my amplification matrix times my homogenized strains. And you'll see here that kind of unlike the fiber, where I have, 5,500 microstrain in homogenized, I have, 9,500 microstrain in the matrix. So there's our factor of 2, give or take. You can see these numbers are on the order of 2 on the diagonal. So that's why the strain in the matrix is about twice as large. Okay, but I need to calculate my volumetric strain, or J1. Well, that's just equal to the sum of the normal strains. So I have in the matrix phase about 5,000 microstrain volumetric strain. And I need to calculate my mean stress. In order to get my mean stress, I need my bulk modulus, K of the matrix. So K is equal to what? E divided by 3 times 1 minus 2 times Poisson's ratio. And so that's my bulk modulus. And so my bulk modulus times my volumetric strain gives me my mean stress. So about 2,800 mean stress. And then my volumetric strain at 0 stress is going to be 25% beyond the J1 that I have. So somewhere around the 0065, give or take. Okay, so let's go ahead and put this particular information into my, so these are the numbers I'm going to put into my material model. I'm going to go ahead and save this just because we'll save this as an Excel sheet now. I'll just leave it in the folder, my material model library folder where I have it. But now I'll have the Excel sheet for future reference if I ever need it. But we're going to come back here to the matrix phase, and the mean stress we said was 2,800 give or take, and our J1 was 0065 give or take. Okay, so I've got all of the brittle behavior covered in my tests. So let's go ahead and perform another forward homogenization out with these new numbers and kind of see where we stand. So we'll save this and then rerun again. Okay, so the next iteration of my virtual simulations is done, and I can take a look at those in Excel. Just to show you that they actually did run. We'll look at these in the final PowerPoint, this particular slide in the final PowerPoint now. So let's flip over to the PowerPoint. And what we'll see is, at least for what we characterize, the fiber brittle and the fiber instability and the matrix brittle, we see that these numbers are matching the experimental data right on now. So 315, what you see here, 0 degree tension, LT. 210 exactly for the LC, longitudinal compression. My transverse tension is right at 7,000 now. And the one that is still not going to match is the matrix ductal, because I haven't inverse characterized that. So my gray curve here, I still need to inverse characterize that particular specimen. Okay, so let's start doing our inverse characterization of the matrix ductal behavior, or the matrix plasticity parameters. We get this from the in-plane shear test specimen, which is our 45 minus 45 tension. It has full nonlinear behavior. Homogenized, we can think of these curves as a typical plasticity curves with a yield stress, a tangent stress, a hardening slope, and a plastic strain limit. Nothing surprising or that isn't well understood in our engineering language there. But what we really want is the yield stress, the tangent stress, the hardening slope, plastic strain limits of the matrix itself. And so we need to do our amplification again. Only we're not going to do this since it's nonlinear. We're not going to do it by hand. Only the linear ones are easy enough to do by hand. That's why I did do those. And again, just to reiterate, because I think it's educational and instructive to understand a little bit about what's going on behind the scenes. This one is not reasonable to do by hand. So we're going to let the program go ahead and inverse characterize this curve in. Okay, so the very first thing we need to do is we need to calculate an initial yield stress and an initial tangent stress. And I want to operate on this linear curve. So that's easy enough to grab the yield stress out of that. But for the tangent stress, what I do to get it, because I want to operate on this linear curve, is I draw my tangent curve, and then where the tangent curve crosses the tangent stress, where it would be, I draw a horizontal line over to my linear curve, and I drop down from there because I want to operate on this curve. It's just easier, and that's what I say is my tangent strain to begin with. And so what we should notice is that I'll get kind of 9,000 and 24,000. I'll go ahead and actually do this. So in the data folder that I give you, there should be a start folder, which contains all the start files, and this T72510 uni contains the initial data of this in-plane shear test specimen right from the data report curve. So this is nothing more than that curve data already put in for you. And if you go to this TVG tab, tau versus gamma tab, we can just go ahead and do this. So I actually just do it kind of graphically. I go ahead and draw a line here for my slope. I always give my lines that I'm using for construction lines as little dots. We'll go ahead and draw a line straight vertical down through that. I should be at about 9,000 microstrain, give or take. For the yield stress, right where I start deviating. Let's go ahead and create another line for my tangent slope here. I usually undercut it a decent amount. And then I can draw my horizontal line from here over to my linear curve again, just so I can operate on the linear curve, and we'll drop our line straight down from there. And I should be somewhere around 24,000 microstrain. Okay, so that's how I get those initial numbers from that curve. 9,000 microstrain for yield and the 24,000 microstrain for the tangent strain that I'm going to operate on. Okay, the next thing we need to do is I need to get these numbers in the matrix. So I need to understand, well, what is the stress, the yield stress in the matrix and the tangent stress in the matrix at these homogenized strain values? Well, we know a few things that we learned. So the matrix, the strain in the matrix is about 2 times the homogenized strain. And if I want to get the normal strain in the matrix, given the shear strain in the matrix, I need to divide by 1 plus the Poisson's ratio. Actually, you solve this equation with the 1 plus V over here, but you can transition this around. If you go back to session 1, you'll see this equation on one of the slides. And then once I have the normal stress in the matrix, I get my normal strain in the matrix. I can get my normal stress in the matrix, and we're off and running. So for our material, our Poisson's ratio of the matrix and our Young's modulus of the matrix are as given here. So that 9,000 microstrain transitions into 18,000 microstrain and shear in the matrix, and that 18,000 microstrain of shear in the matrix transitions to 13,400 microstrain of normal strain in the matrix, and that normal strain multiplied by the modulus of the matrix ends up at 6,930 psi of normal stress at yield in the matrix. So it's just a way to figure out, what is going on in the matrix phase. I can do the same thing with the tangent strain. So I'm staying on that curve because I picked off that strain. My stress value will be pretty close to the stress value at the tangent that I'm looking for. So these are all just initial numbers. And when I do that, I end up with 18,480 psi of stress in the matrix at the tangent. And then I need a initial hardening slope. So I normally start at about 2% of the modulus of the matrix. You can see these things aren't quite a hardening slope of 0. They're not quite perfect plasticity. So I normally start at about 2%. So that would, 2% of 51,000 would leave me with 10,320. So these are kind of going to be my initial values that I'm going to plug into the orthotropic damage and rate independent plasticity law for the ductile portion of it, values 1 through 9, which are nothing more than this curve. The second piece that we need to do is, and let's just go ahead and do that actually while we're at it. So I'm going to go ahead and grab this. Let's go ahead and flip over to our inverse characterization now. I don't know that my numbers, let me save this and then go to my inverse characterization. The numbers didn't save. So what we're going to do is we're going to save this step. We're going to close out and we're going to come back in. And now in my inverse characterization, yeah, I have the numbers from the forward homogenization tab. Let me make this a little bigger just so we can work with IDs 1 through 9. So my initial value of the yield stress is going to be 6,930 as I calculated from the curve. My tangent stress is going to be 18,480. My delta, I normally start with a delta around 25, give or take. For these kinds of specimens, again, it's anywhere between like 0 and 500, but these specimens are going to be somewhere around the 100 or below. But we'll start at 25. It's going to be an active parameter. And my hardening slope, H, is going to be 10,320 PSI. All the other values are fine as they are. I'll just type them explicitly. Theta of 1, that just means I have no hysteresis. A beta of 0.15. And I'm going to set my plastic strain limits to 1 and 1.1, which basically means I'll never hit them. I don't want to inverse characterize a plastic strain limit at the moment. Okay, and the tangent stress, the delta, and the H are going to be values for which I don't really know. The yield stress, I know very well. It's a linear number, so the calculation I did is very accurate. But the tangent stress, the delta, and the H are pretty much unknown parameters, and it's going to set the lower and upper bound based on that 25% that I have in the settings. So the auto calculate bounds at 25%. You can change that, but 25% is pretty good. What we need to do now is I need to inverse characterize these numbers to an actual curve, but that curve is coming from my test 3, which is my in-plane shear. So I need to enter in the curve for this particular test. The problem is that this test, the curve that we get from this test is not the shear stress strain curve. The curve that we get from that test is a normal stress strain curve. And so we post-process that through the ASTM and ISO standards to a shear stress strain curve. So we need to unpost-process it back to the normal stress strain curve. Well, that's easy enough to do. The normal strains is 1 over, the shear strains over 1 plus the Poisson ratio, and my normal stresses are 2 times my shear stresses. The IPS specimen has a Poisson ratio of 0.785. That's the plus or minus 45. It's got a very large homogenized Poisson ratio that we have to use in these calculations. So all we have to do is go back to our original data. I'm going to put the Poisson ratio of the IPS specimen in here, which is 0.785. I could also get that number directly from my homogenization, so you know that this number didn't come out of thin air. If I go to linear characterization and I go to my results here and I go to my IPS specimen, my plus or minus 45, I'll make this bigger for you. What you can see is 0.786 actually is the Poisson's ratio. So that's where that particular number comes from. Okay, so I need to get the normal strains, and I need to get the normal stresses. Okay, so the normal strains is going to be the shear strain divided by 1 plus the Poisson ratio. And I'll just go ahead and fix that, and we'll set this as our microstrain. So I always put 6 digits to help me just see microstrain better. And our normal stress is going to be 2 times my shear stress. And we'll go ahead and put that that way. And then we'll just go ahead and copy this down for all the data that we do have. Okay. And so this is my normal stress strain curve. And if I wanted to go ahead and plot that, I could just go ahead and plot that just to look at it. So we'll add another curve here. Our normal curve, the x's is my normal strains, and my y's are my normal stresses. Okay, and I've got my my normal stress strain curve. So this was the curve that the specimen actually, that the test machine actually recorded from the test specimen itself. And then we post-processed with ISO or ASTM standards down to the shear stress strain curve. But this is the curve that we need ultimately. So we're going to take this curve and we're going to put it into a DAT file. So we're just going to open up any particular text window, and we're just going to go ahead and paste it in. And this is the kind of space-separated XY data for this particular curve. So we'll save this as, we'll go to our desktop, our Multiscale Designer, start. I'll just call this the T700 2510 IPS SVE .dat. Okay, so I just saved this particular file, and we're ready to go ahead and use that now to load it into Multiscale Designer. So back in Multiscale Designer, I want to load that stress strain curve in. I got to go to my IPS test, so make sure that you stick to your IPS test, because this is the curve for this test that I want to load in. And we can say import test data. And if I go to my location again, so it's under start, there's my T700 2510 IPS stress for strain data. And when I loaded in, it went ahead and loaded in the data points. I asked for 20 data points, which is fine. It's going to actually interpolate. I had much more than 20 in there. If I asked for 30 data points instead of 20, you can ask for as many as you want, and I import the test data again, it will just interpolate to 30 data points now instead of 20. So now I get 30 data points in there. So however many data points you want, go ahead and put that number in there. It also figures out the maximum strain from the test data, and everything else can remain as is. Okay. Last thing we need to do is we don't need to run all of those tests. So in the running list here, we can turn off all of the tests except for the IPS. It's the only one that we're inverse characterizing to. If I had other curves for other tests, then I could turn those on, but I only have this one curve for this one test. So now what's going to happen is I've given the curve here. It's going to change these parameters, the yield, the tangent stress, the delta, and the hardening slope, until it matches the curve. And it's going to do that. We're going to do that with an ant colony algorithm, which is the genetic-based algorithm. And it's going to do that until it sees an error less than 32. The sum of the error at all 30 points has got to be less than 32, which is a pretty low number when we're talking about things in the 10,000s. And I'm just going to start with 50 iterations. So try 50 genetic spawns. So you can change that number. I just don't want it to run forever. So let's go ahead and launch this optimization, and let's see what comes back. Okay, so our optimization finished, and you can see at the end of the 50 genetic algorithm spawns, I ended up at a little over 1,000 total error, which is still very, very small. That's the total error at all 30 data points is 1,000. And you'll see that when we plot this, it's a very close fit. And our final active parameters, again, were given here. But when we close this out, we'll do it again and update initial values, and our optimized values will be loaded in. So we'll go ahead and close out our optimization window, and we'll go ahead and update our initial values to get the optimized values loaded back in. But let's also take a look at the fit of where we stood right now. So we'll go ahead and look at this in Excel. We'll click Excel. And what that will show you is the simulation versus experiment. So the simulation is the blue curve, and my actual experimental curve is the orange curve. And you can see that I have a very, very good fit now between the two. Very close. This is actually a fantastic fit as is. So I'm very happy with this fit, which means I don't have to run another iteration of the optimization engine to try and get it a little closer. Although you could if this was not close. Okay, so we got a good optimization fit now. We've inverse characterized all of our parameters. So we're going to go ahead and save this step. We're going to close out. And then I always do one last forward homogenization. That's, again, good practice. We always start with a forward homogenization, do our inverse characterization, and then end with a forward homogenization. So all my final values are now inverse characterized into here. And I'm going to turn on all my specimens again. So I had turned off a few of them, but we're going to turn on all of them again. And I need to, I think some of my numbers have changed. So I think it set a lot of my mechanical increments to 20. I'm going to put those back to 200, and it definitely changed my IPS. There we go. So we'll just get the data back to what it needs to be. We're all good. We're going to go ahead and do our final forward homogenization run just to get our final curves and verify one last time that it matches our experimental evidence. Okay. So now when we plot these in Excel, and I go look at each of these individually relative to the test data, you'll see that each of these is exactly line on line with the actual test data. Okay, I'm complete with this step. I have a complete material model now. So I save always and then close out, and this particular material model is now done. Okay, let's talk a little bit before we close out completely about verifying our multiscale material models. So what we want to do is we want to run this material model against something that we didn't use to inverse characterize it to. So that something is actually available. So if you look at the NIAR agate data for this T72510, there's a second data report, which is a data report that covers unnotched tension, compression, open hole tension compression, bearing bypass, etc., for various laminates. In this case, a 50-40-10, a 25-50-25, and a 10-80-10 laminate of these stacking sequences here. And the data, we'll just look at the data for the 25-50-25 just as an example of a verification effort. And we're looking at the room temperature mean values, and we can see those values here. So we've got for the tension, unnotched tension specimen of the 25-50-25, which is this kind of quasi-isotropic 45-0 minus 45-90 3S laminate. In tension, we've got a modulus of like 6.9 MSI and a strength, looks like of like 98 KSI. And then in compression, we've got a modulus of like 6.4 MSI and a strength of like 96. So this will be bigger in the actual data if you go look at it. But what we want to do is let's add one more laminate, and this is the exact laminate for that tension compression specimen. I'm going to call it unnotched tension 1 and unnotched compression 1. And we're going to add two more virtual simulations, simulation 6 and 7, which are tension and compression of this laminate, which is not a laminate that I used to create this material model on. And we want to see how close does this prediction get to the actual experimental evidence, not having inverse characterized to these particular numbers. Okay, so let's go back to our material model here. We'll go back to the linear characterization, and we'll add a fourth laminate. That fourth laminate will be, we'll actually do our 4 plies symmetric. So it's a minus 45. Well, actually, what is it exactly? It is a 45-0 minus 45-90. So, and we can do our 12 plies. So it's a minus 45, let me just look at that one more time. 45-0 minus 45-90. So it's a 45-0 minus 45-90. We'll repeat that 3 times. So 45-0 minus 45-90, and then 45-0 minus 45-90. And then that whole thing's symmetric. And we've got our fourth laminate. So let's go ahead and run our forward homogenization linear stiffnesses again. This will just give me the stiffness of that fourth laminate. And when I look at the results, what we're going to see for our fourth laminate here is what we should be is let's see, 6.9. And what did I have here? Oops, let me get my results back again. Yeah, so 7.0. So 6.9 versus 7.0. Very, very close to the actual experimental data. And in compression, I had 6.39. I think the data is 6.4. So if I go back, look at the data, it's 6.4. So again, very, very close in stiffnesses. So you could say that is validated very well. It's actually most stiffness predictions are going to be accurate within plus or minus 5%. These are actually much closer than that, but very comfortable saying within plus or minus 5. Okay, but let's take a look at the strengths. So we can close that out. We can go back to our nonlinear characterization, our virtual test lab, and I can define two more simulations. So simulation 6 is going to be unnotched tension of my laminate, my quasi-isotropic laminate. I think that's laminate 4. Yep, that's my laminate 4 here. And I'm actually going to make that this 006 thickness so that it's got the right thicknesses now for the exact strength. We're going to pull that to 2%. I don't know how far it's going to go, minus 200, 10, and 200 increments. And then I'm going to do my compression version of this. So my unnotched compression. Laminate 4, we're going to go minus 2%. Okay, so now when I go ahead and run this, it's going to run, I could just run simulations. Well, I'll run all the simulations again, although I just have to run 6 and 7. So we'll just run them all again. No big deal. But now when simulations 6 and 7 are run, those will be actual predictive simulations because I didn't use those simulations to inverse characterize to anything. And we'll see how those particular results compare relative to the test data. Okay, all 7 simulations are completed now. And if I look at these 7 simulations, I'm actually interested in the unnotched tension and compression. So I'm interested in my later tabs here. So unnotched tension, you can see that I'm at 102 KSI, and in compression, I'm at 78.6 KSI. And so if I go look at that relative to the data is 98.2 instead of 102, still very close, definitely within plus or minus 10. And in compression, 78 versus 79, again, very, very close. So I give you the validation of some of the other specimens here, the 1080-10 and the 50-40-10 laminates. They are all within plus or minus 5 or plus or minus 10 stiffness and strength, respectively. So just a little exercise to show how you should go through verification of your particular material model. Once you've gained confidence with that particular material model, then you can start to reduce the amount of verification that may be necessary and start using it to actually do virtual simulations for various properties or results that you're looking for of various different laminates. With that, this completes the short course for the Introduction to Multiscale Designer for continuous reinforced unidirectional materials. I wanted to thank you for your attendance.